We have studied different type of flip-flops, flip-flop conversion, counters, shift registers in the last some lectures, and today we are going to discuss about synchronous sequential circuits. And in this particular lecture, we are going to cover the sequential synchronous circuit analysis and synthesis. As far as analysis is concerned, in analysis we are given with the circuit and we have to find out that how the circuit will behave under different input conditions. On the other hand, when we are going to synthesize a circuit, that means we have to design that particular circuit. For the synthesis, we are either given a block diagram or a word problem or a timing diagram, and depending upon that particular diagram or the word problem, we have to design a sequential circuit which will behave like the given specifications. So let's move with the basics of the synchronous sequential circuits. Now the first part is analysis of clocked sequential circuits. The process for the analysis is same as we have done in the combinational part. First of all, determine the state equation from the given circuit diagram, that is known as transition equations. With the help of transition equation, determine the state table, that is the transition table, and with the help of the transition table, draw the state diagram. So we are given with this sequential circuit and we have to draw the state diagram of that particular circuit. Now with the help of an example, we are going to discuss how all this is accomplished. Suppose we are given a sequential circuit we using a D flip-flop. Here we have two D flip-flop. For output of the first D flip-flop is A. Here it is denoted by A and A bar. Output of the second flip-flop is B and B bar. And look at the clock. Clock is common to both the flip-flops. That means it is a synchronous circuit. Now we have one input X, that is the external input. We have one output Y, that is the external output. And A and B are the outputs of the flip-flop. We have some feedback paths. The output is fed back as an input. So this is an all which is given to us, and we have to analyze this circuit diagram, that how this circuit will behave under different input conditions. So with the help of the procedure we have discussed above, that is determining state equation. So the first step will be to determine the state equation for DA and DB. And as we know that the output of the D flip-flop is equals to the input, that is the next state will be the input. So directly we can find out here the equation for A and B like this. So the equation of A t plus 1, here t plus 1 denotes the next state. So here it is A. So A t plus 1 is, A is fed back here, A t x t or x and bt. So the equation for dA or AT plus 1, because dA and AT1 will be same, as we know that the output of the flip-flop is equals to input as in case of the D flip-flop. So we find out the state equation as AT plus 1 equals to AT xt plus BT xt. Similarly, we can find out the equation for B. So BT plus 1 will be, here it comes from, here it is X. So this line is missing, that is X and AT bar. So BT plus 1 is A bar T and XT. Similarly, we can simply write it like AT plus 1 is AX plus BX, BT plus 1 is equals to A bar X, and similarly we can find out that Y equals to A or B and X bar. So these are our state equation, or in case of the sequential clock circuit, we say it as transition equations, because these equations define the transition of the flip-flop from one state to the next state. So our next step will be to find out the state table, and here we go how to find out how to draw. the state table, we are given AT plus 1, we have find out from the circuit diagram. AT plus 1 equals to AX plus BX, and BT plus 1 equals to A bar X, and Y equals to A plus B and X bar. So with this help, so here are three inputs, A, B, which are the present state, and X. So three inputs are A, B and X. We note down 8 possible combination for the all inputs starting from 0, 0, 0 to 1, 1, 1. This is our first step. And with the help of these equations, by putting the values of A, B and X, we can find out A, B and Y. So for the case of the 0, 0, 0, suppose, so here A is 0, B is 0, 0 and 0 and 0 is 0, or 0 and 0. So the AT plus 1 will be, for this particular equation, will be 0. Similarly, B is equals to 0 bar is 1 and 0 is 0. So B is 0. Y is 0 or 0 is 0 and 1. So 0 and 1 is 0. So similarly, we can find out the different values of the next state and the output. Take another example. Suppose A is 0, B is 1 and X is 1. So A is 0, 0 and 1 is 0, or 1 and 1 is 1. So 1 or 0 is 1. So A is 1. Similarly, we can find out B. A is 0, so A bar will be 1. 1 and 1 is 1. So here it is 1. A is 0, B is 1. 1. X is 1. That means X bar will be 0. 1 and 0 is 0. So Y is 0. Similarly, for the different input combinations, so always in case of the sequential circuits, your input will be all your present state, how many flip-flops you have been using, and all the external inputs will act as a present inputs. And we have to find out the next state and the output. So here is your state diagram. So state table. State table represents present state, input combination, and the next state and the output. So I can represent this state table in a more convenient way as, so present state is AB, next state is AB. For the different input combinations, for X equals to 0 and X equals to 1, we have separated out. Similarly, output is Y for X equals to 0 and X equals to 1. And this table is simply drawn from here. You can see for this particular AB is 0, 0. That is the present state. One is input is X equals to 0, then the next state is 0, 0. When input is 1, the next state is 0, 1. And for both cases, output is 0, 0. Similarly, for the input present state 0, 1, we have again two combinations 0, 1. One for X equals to 0 and one for X equals to 1. When X equals to 0, next state is 0, 0. When X equals to 1, next state is 1, 1. For X equals to 0, output is 1. For X equals to 1, output is 0. In this way, I have separated out this state table. So AB, present state, and the next state for both inputs, and output for both inputs. So this is a more convenient way to represent a state table. And with the help of this state table, we have to find out the state diagram as, suppose this is present state 0, 0. So present state is 0, 0. So we have 4 states. So I have denoted 4 states 0, 0, 0, 1, 1, 0 and 1, 1. You can put your state anywhere. The diagram shape may be any. It is not that it will be placed in a square. You can place it as you want. So with the help of state table, whenever present state is 0, 0 and next input is 0. So next state is 0, 0. The present state is 0, 0. Input is 0. We have not input oblique output. This is input oblique output. Whenever X equals to 0, next state is 0, 0 and the output is 0. So next state is 0, 0. So I have, this is the arrow shows the next state where it is terminating and the output is 0. With present state 0, 0, if input is 1, X equals to 1, then the next state will be 0, 1 and the output will be 0. So present state 0, 0, next state is 0, 1, here it comes 0, 1, input is 1, oblique output is 0. Now we look at 0, 1. If present state is 0, 1 and input is 0, when input is 0, next state is 0, 0 and the output is 1. So here goes present state is 0, 1, it goes to 0, 0 with input 0 oblique output is 1. With present state 0, 1, next state is 1, 1 when input is 1. So input x equals to 1, next state is 1, 1 and the output is 0. So from 0, 1, input 1 oblique output 0, next state is 1, 1. In this way, you can draw the state diagram for different 4 stages. So we started with the circuit diagram and we end up with the state diagram. This is known as the analysis of clocked sequential circuit. So for the analysis purpose, you have to find out the state diagram. Let us take another example. Suppose we are given a circuit diagram with JK flip-flop. Here we have used 2 flip-flops, again A and B. We have single input X and some feedbacks. You can see again the clock is common, that is circuit is sequential. So with this help, as next state is not equals to J or K, that means we have to find out the state equation for the JA, KA and JB, KB. So here are the equations. JA equals to B, KA equals to B X bar. These equations are directly drawn from the circuit diagram. JB equals to X bar and KB equals to A XOR X, because XOR gate is present at the input of the K. So with this help, we have to find out the state table. Again, 2 flip-flops, 2 inputs A, B and 1 external input X. We have to write down 8 possible combinations from 0, 0, 0 to 1, 1, 1. We have expressions for JA, KA, JB, KB as we have find out in the last slide. So here is JA is B, KA is B X bar, JB is X bar, KB is A XOR X. So these values are directly drawn from the state equations. JA equals to B, KA equals to B bar, B, and with the help of the input JA and KA and the present state, the next state A and B are find out. Suppose JA and KA is 0, 0, that means store. Now with the help of this, we have to find out the state equations for the next state. So here A T plus 1 comes to be J A bar plus K bar A, and this is achieved with the help of either K map or with the help of tabulation method. The state diagram. From the state table, we can directly draw the state diagram having present state, input combination and whatever is the next state. Here you can see at the circuit diagram that there is no output. So only input is there. So present state is AB, next state will be AB and input X will decide that how the circuit will jump. Next states are decided with the help of AT plus 1 and BT plus 1. So again in this example, we started with the circuit diagram and we end up with the state diagram. So this is known the analysis of sequential clocked circuit. Come to the next point, as these all circuits are, or the state diagrams are known as machines. So, or models. So, in the digital circuit or the sequential circuit, we have two types of models. One is the Mealy model, and the next one is Moore model. The most general model of a sequential circuit has inputs, outputs, and internal states. Internal states are the present states. So there are two different models, Mealy model and Moore model. The difference is how the output is generated. The model is defined on the basis how the output is generated. Now, in case of the Mealy model, output is a function of present state and the input, while on the case of Moore model, output is only a function of present state. So the present state will define the whatever is the output. So these are your basic sequential circuits, as we have discussed when we started with the sequential circuits. We have inputs, we have outputs, we have clock pulses, some combination logics, your gates, and some flip-flops. And depending upon their transition, if the output is a function of present state, then it is known as Moore machine. If the output depends only on present state and the input, that it is known as Mealy machine or Mealy model. Now let us talk about the Mealy model. We have input combination circuit, we have some flip-flops, and for the output we have some combination logics. And the output of the flip-flop is the current state. When we observe the state diagram of the Mealy machines, the observations are as follows. Output can change asynchronous to the clock because output is a function of combination logic, and the combinational circuit does not require any clock pulse. The output delay with respect to the clock is unpredictable, and further it is difficult to do the timing analysis of the Mealy machine. On the other hand, this is the Moore model, and the observations from the state diagram of the Moore model is that output changes synchronous to the clock until unless there is no next state is given to the combination circuit with the help of the clock, the output will be same. The output will only be changing whenever there is an active clock. The output delay with respect to the clock is predictable, because whenever clock is given to the flip-flop, then only the input to the combination circuit related to the output will change, and easier timing analysis for the Moore machine. So there will always be a question in your examination regarding Mealy machine and the Moore machine. So how to differentiate between them? So this is how a Mealy machine and Moore machine looks like. Next, we come to the state reduction techniques. For the sequential circuit analysis, we are given with the circuit diagram and we have to find out a state table or a state diagram. For the sequential circuit design, state diagram is given or the state table is given. We have to find out the circuit, we have to draw the circuit diagram, and that is known as the synthesis process. There may be some redundant states which are existing in the state diagram or the state table. By eliminating the redundant states, that is, reduce the number of logic gates and the flip-flops, because the number of states are responsible for the number of flip-flops and hence the number of gates. So with the elimination of the redundant state or with the reduction of the redundant state, what we are doing, we are reducing the cost of our final design and hence the complexity of the design. So how to eliminate these redundant states? The two states are said to be equivalent if and only if each member of the set of the inputs they given exactly same state on an equivalent state. So two states are said to be equivalent if we give the same input combination to that state and the circuit goes to the same next state and produces the same output. In that way, we say that these two states are equivalent, and when two states are equivalent, one of them can be removed. So this is the way how the redundant states are removed, and we save the designing time, designing cost, and complexity in our final design. So this is how we have to kept in mind every time when we are dealing with the state diagram, that the redundant states must be removed, and the process of removal of the redundant state is known as state reduction. And the benefit of the state reduction is that we are finally decreasing the complexity of the circuit. We are reducing the hardware, that is gates and the flip-flops, and further we are decreasing the cost of our final design. Now suppose this state table is given to us, or we have find out this particular state table, and the corresponding state diagram is like this. We have 5 states A, B, C, D, E. We have one input X and one input Y, so the output Y. So here you see that the output is written into the state A/1. So until unless a machine is in state A, that is the present state, the output will be 1. So it is a Mealy machine. When input present state is 1 and input is given 1, when input is given 1, it is going to C. So present state A, input is 1, it is going to C. When present state is A and input is 0, it is going to D. It is going to D, and in D output is 0. When it is in state D, output is 0. Whenever it is in state C, output is 1. So this is just for an example, what the state reduction means and how it will benefit to design our final circuitry. Now I have tried to reduce this state table like this. So you can see when I look into state B, A and C, if A is equivalent to C, you can see that the output of both state is 1, 1. With input, when if we are in state A or we are in state C, the next state for the input 0 is D, and next for the next state for input 1 is either C or A. If A or C are equivalent, the both state are equal. So I denote by P. Wherever there is A or C in the table, I have written as P, and both states are reduced or merged into a single state, that is P, and the next state is D or P, and the output is 1. So this is how there are two redundant states A and C. The both of so work of both state is same, that it is going to next state either D or C and producing output 1. So I have reduced two states into 1. Similarly, when you look into B and E, so B and E, here A is equals to P and C equals to P. So here both are P, output is 0, and here it is E and B. So B and E we are comparing. If B and E are equivalent and we replace B and E in this total table by Q, then the next state will be P and Q, and the output is 0. So with the help of reduction or removal of the redundant state, we are left with only 3 states, P, Q and D. Here are the 5 states. To represent 5 state, we need 3 flip-flops because 3 bits are required to represent 5. And to represent 3, we need only 2 flip-flops. So what we have done, we have reduced 1 flip-flop in the circuit, and as well as 1 flip-flop is reduced. That means some external gates are also reduced. The circuit will be less complex. The cost of the circuit will be less. So here is the state diagram. of the reduced table. So this is the way how the reduction takes place and how it finally affects the total design of the circuit diagram. So I think let's stop our class here.